Hello, everybody. Thank you for coming. So I'm David Berg. I'm on the Metaflow team, and I remember working on the initial version of JDev's project with him something like 5 years ago. So a lot of the features we have in the Metaflow data frame he talked about were like inspired from JDev. Anyway, I'm David. This is Fan over here. We're going to be talking about something new, Metaflow functions. I'm going to kick it off, and then Fan's going to finish it off with like some practical use case. So this is new. This is not built. This is something we've been designing and working on, and we have some prototype. So if you think it's awesome or it sucks, please let me know afterwards. But anyway, the idea here is that we want to build some infrastructure and experience for serving member traffic with Python-based models. Now, you may be wondering, I thought you guys said earlier that you used Python and Metaflow all over the place. That is certainly true. We have like hundreds of models running in production, including APIs from the hosting deployment that Roman talked about. But we do have actually special infrastructure for our biggest member tasks, like the row ordering when you go to Netflix.com. That is handled by an extremely high scale production system, teams that operate it to make sure that you have a good experience. And so now what we're foraying into is the first time of using Python in those systems that handle those really important business cases. I used to be a researcher a long time ago at IBM Research. And so, as a researcher and a scientist, you spend a lot of time developing your model. It starts out as a little function. I had asked the generative AI to generate a epsilon function. I don't think it quite got it right, but that's okay. And then later on, you develop this thing and it becomes like a whole system, like this robot, and you're kind of attached to it, and you kind of raised it and are growing it up. And then eventually, like, you've shown enough utility that you can start to work this into whatever the business offerings are. And then there's some platform team that tells you need to do dependency management in their way. And then you have to package your code in something called Docker. And then you have to can't just give them your model, you have to write your own API endpoints. And then, well, wait, you just started writing code that was different from the code that you wrote for your offline. And so there's this whole parity issue, and it makes you pretty upset over time. And the older I get, the less and less I am able to tolerate these kinds of upsetness. So we started to think about something new. So what if we had something lightweight that was in between, that helped you transport your model from your kind of developer workbench and workstation and put it into the real world? And maybe it's like something in between the model on your workbench and the actual production one. And so, we're thinking of some sort of a lightweight encapsulation. And what should this lightweight encapsulation do? Kind of want to hermetically seal your model like this little function that's living in this spacecraft so that it can travel around. And what kinds of things might you need? You might need to take your code, like your actual model code that you wrote, the environment, that is like the software packages, and then the parameters, the things that you produced when you were training. And you'd like to kind of bind all these together, but maybe you don't want to worry about complexities like communication interfaces, like whether it's gRPC or REST. That's more of a platformy thing than it is a data scientist thing. Okay, and you may be asking, well, is this really a big problem? Can't you just write one Flask API and then be done with it and never revisit it again? Well, maybe. I guess that kind of works. That is what most people do. But that doesn't travel as well. It's not as portable. So I would like to use that same function I wrote both back in my development environment. Give it to somebody else so that they can use it in their development environment, but maybe so they don't have to worry about how they got the parameters or the environment, because you kind of encapsulated all this thing. You may also want to run it in somebody else's workflow. Maybe you want to export the functions to Ray or Spark for distributed computing. And then there is a plethora of kind of front-end sort of request handling frameworks in all languages, and your platform team will likely change those out, over time. And so we want to have sort of one encapsulation that can work in these different environments. So I'm going to show you a little bit of code about how it might look, and I'll try to describe how it works as I show you the code, and then we'll come back to the bigger picture. Okay, so here, this is the anatomy of a Metaflow function. It really only has two interesting parts from any other function. It has this decorator at function, which I'll talk about in a little bit. But the most important thing to notice is that it takes this argument, this task object. So if you're not familiar, a task object is something you can get from the client in Metaflow. It refers to what happened during a task that you run. And a task is just some node in the Metaflow graph. And it includes, beyond all the information about whether the task succeeded, the logs and whatnot, it also contains the data artifacts. In the Metaflow parlance, data artifacts can be really anything, but let's just say for the context of this talk, they're the model parameters. So you see in this really dumb function, adder, it just takes two numbers together, adds them with a constant and returns the result. And that constant is coming from the task.data field in the task object. So the way this would work is you would train your model offline, you would get that task object, and then you can pass it to this function. Other than that, it just takes other parameters that normal functions take. That all sounds fine, but when I give someone else my model, they don't have that task object, right? I expect to encapsulate the aspects. What do I want to encapsulate? I want to encapsulate the parameters. I also want to encapsulate the environment. That means the software packages I used when I was getting those parameters. Say PyTorch, for instance. And so let's look at a couple of things. The task objects actually provides those parameters, and it provides the environment specification. It can be bound to a function that has already been written. And if you've heard of this probably dates me, but a very popular style of programming back in the day was like functional objects, functors, if you've heard that term. That's kind of what's produced here. So when you bind a task plus my adder function together, you get back a new function. That new function removes the task part. It's like bound it to it. So the user is only exposed with the arguments A and B. I can then later export that function. Exporting it throws it into S3 someplace. We can talk about how the packaging works. And then it's kind of an immutable function blob in S3 that other people can use later. And I'll show you what the syntax looks like. So this is how you would re-import a function. So you can just import Metaflow functions, call function.import, give it that reference that was returned by the export, and now you can use this function in your own environment. This doesn't really seem very impressive from the code that I just showed you, but let's maybe talk through a little bit what's happening. So as I had mentioned, you bind together the parameters in the environment. So that means that if I'm sharing this function with you, I have no idea what packages are installed in your environment. So how can we manage this? Well, we create a subprocess. We actually load your function in the subprocess, recreating the Conda environment or whatever. It's Conda for Metaflow, but whatever packaging system you use. We also load the task parameters, which come from our data store, which Roman showed you a little bit about earlier. And at runtime, it looks something like this graph. So on the purple side, we have the proxy object. That's what you're getting back. So the adder that's shown in the code snippet above. But that function isn't actually, that function that seems like a function isn't actually running your code. It's communicating with the subprocess over a well-known Linux IPC channel. In this case, we use memory maps. So on the green side, what's happened is we've rehydrated your environment, which we knew about from the task object. We've loaded all the parameters, and then this thing goes into a run loop where it takes information from the memory maps, passes it through your function, and passes it back. It needs an IPC format. We use Avro and Apache Arrow, and I'll talk a little bit more about those later. Okay, well, like at scale, this thing is kind of neat, but you could imagine these functions are kind of willy-nilly running all over the place, creating sub-processes. So we have some notion of a function server, and this is a Linux daemon process, if you're familiar with that term. It's basically just a background thing that's always running on your machine, and it offers some control channel and some data channel. The data channel is just what I talked about before. It's the memory maps. And the control channel is just like some simple, dumb socket server that allows a proxy object to ask for information. Something that you can do, for instance, is lease a function. Leasing a function would return you back the name of the communication channel to connect to you. Once you've established a connection between your proxy object and the function server, it works kind of like the slide I just showed you. And this function server, beyond managing the processes, controlling the C groups, all this kind of thing, it also handles log aggregation, functions that aren't behaving well, catching exceptions, and all of those things. And that can be returned, all that information can be returned to the client over the control socket. Let's go back to the bigger picture now. Back to the premise of what we were doing here, which is running Python code in member systems. And this is a rough figure of how the interaction between an external system and Metaflow could work for this use case. So Metaflow in the light blue here is producing task objects. Those can be used with your function code plus the bind operator to build the little spaceship that encapsulates your function. And that includes your user code, the environment, and parameters. The task object already had landed a bunch of information in Metaflow's S3 data warehouse, which is the artifacts, that's like the model parameters and such. The code package, which is like the user code, as well as the version of Metaflow that you were using. The conda environment is all hashed in there. And then we've added kind of one more thing to the data warehouse, which is this function metadata. The metadata is a full description of the function in JSON form. It tells you what module you need to import it from. It tells you exactly the conda environment you need to rehydrate it. It also gives a schema in a universal format like Avro, so that other people can, and other systems can parse this metadata file and understand like how to interact with your function. It also gives an entry point so that you can start the whole function server programmatically. On the serving runtime side, you can imagine something like let's talk about, say, fraud detection, since that was mentioned earlier. You might have some fraud server, and it's maybe talking to some managed serving infra, which is our high performance production servers. And then inside that system, we're actually running the function server. And so the fun part here is, like, since the function server is just a sub-process running a Linux daemon, opening communication channels over standard Linux protocols like sockets or memory maps, then it really doesn't matter what language the stone-colored box is, right? That could be Java, that could be Go, that could be C++, it could be whatever you want to, because it's actually communicating with this function server over a standard inter-process communication. Okay. We don't actually use those simple functions like the ones I was showing you that just add two numbers together. That was just for illustration. This whole system is extensible. So functions are like the core foundation that helps build the little picture I showed you in the previous slide. What we're working on right now is like an extension to that called data frame functions. So JDev had mentioned this nice piece of technology, Metaflow data frame. We use it as a universal way of communicating Parquet, basically, tabular sort of data. And so we built an extension to functions that takes a Metaflow data frame as an input. You can build whatever kind of extensions, your own decorators you want to. In this case, we've added a field called columns that tells us the column names we expect to find in the data frame. So, we can do some static checking to make sure that, or runtime checking to make sure the incoming data frame is acceptable. But you could plug in your own favorite object that people at your company have created. It really only requires that you have a suitable IPC format. Metaflow data frame is Apache Arrow memory under the hood, so they have a suitable IPC format for Apache Arrow. So this is the same dumb A plus B plus constant, but this is actually a little bit closer to how it looks if someone were to write it at Netflix. Okay, Fan's going to take over now, and he's going to tell you a little bit more about how we're going to integrate this function server idea into our Java production system, which is cross-language now.
All right, thanks, David, for introducing Metaflow function and how it supports relocatable computations. Now I'm going to talk about how we actually leverage Metaflow function to enable Python-based model serving in our very JVM-centric serving stack. So this is a very high-level architecture of how our serving stack looks like. The green boxes there are the components we build as a machine learning platform team. As you can see, so the entry point to the platform are for our users, which are the researchers, are this like a model repository and model specs. So we provide a bunch of libraries and tools for researchers to build models using our tools we provide, and then they can publish the model into the repository, and they also can register the model for serving using the config format we provide, which defines like a what, like a when and how the model should be served for what type of traffic and things like that. And once the model is registered for the serving system, the model servers will pick them up. And the model servers are responsible for the execution of those models. And the model server will have all this built-in integration with a whole bunch of data providers within Netflix so that it can supply the necessary data that are required by those models. And in front of that, there's this routing layer, which is sort of the entry point to the entire serving system. All the business applications will interact with the routing layer when they need to use certain models. They can pretty much just ask for the model they need, and they will get the response from that model. And when the routing layer do the routing, it has all this knowledge about the A/B testing as well, because it has this built-in integration with our A/B experiment platform. So this entire stack is our paved path for like member scale model serving. Is like very GVM centric. I think all the components you saw in the previous slide are pretty much GVM based, and it's very high performant. It's kind of battle tested for all the very high scale model serving that meets the needs to serve Netflix member base. So in order for our researchers to onboard their model to this serving stack, we actually created an in-house model schema. This schema make it easier for the serving system to understand the models. So whenever it loads a model and look at the schema, it know what need to be for this model, like what data it's required, how to do feature computation using the data, how to execute the ML algorithm, all of that. So the schema defines all those behavior. And in order for like the researcher to actually build models following that schema, we provide a whole bunch of tools for that. For example, we have the tools for you to get data for both online and offline. We have tools, we have the library for you to define all the different components. Like how do you define data? How do you transform the data? How do you compute features from that? We have a GVM library to do that. You can define your own logic using the library. And we have a rich set of tools for offline, where you can do all this like data manipulation, feature engineering, and training at scale. Again, this is the paved path, and everything is sort of done in GVM. But this system served us pretty well over the year, but there are growing needs for a Python-based model serving. Right. I think I'm jumping too fast. Somehow one slide is missing. Yeah, so basically, like we have this need for a Python-based model serving now, mostly because we like people. First of all, people love the ease of use UX provided by Metaflow. This is super important for all this brand new use cases that's coming up that want to leverage ML, because the Metaflow UX is pretty much very well fitted into all this data science and ML needs, and is very natural for all this like idea to experiment, like quick iteration from idea to experiment. Is compared to our GVM stack, the kind of ramp up time on that is much better. And but the key problem is that we already have this very mature serving system. We don't just store that away and go with Python altogether. We still want to retain all the power of our serving system, but we want to enable this Python-based modeling experience. And this Metaflow function fits pretty well into our needs to enable that. So now instead of authoring all these components in Java, we now have a new set of abstraction on top of Metaflow function where you can author all these components in Metaflow function. And you can use whatever library, Python libraries you prefer in your function, and Metaflow can help package everything into this function abstraction. And as David mentioned, you can even move that to other systems for you to execute those functions. And we defined a new model schema that bridge the serving system and Metaflow functions. So in a similar way as our old model schema, now the serving system can understand what's the data needs from all these functions, how to execute the functions, and it's when the serving server load the function-based models, it know what to do. And as like David pointed out, we have this function server idea, which manage all the functions in the server. And for the serving server itself, it pretty much just interact with the function server when needed, using all the IPC channels exposed by the function server. Yeah, I think somehow these two slides flipped order. But in any case, so this is the serving system after we introduce Metaflow function into the picture. If you remember the previous slide, it's pretty much look exactly the same. All the major components are still there. The only change is that when you look inside those model servers, it's not a pure JVM service anymore. It integrates with this function, this Python-based function server, which know how to load the functions, how to run all the functions. It exposes the IPC channels for the JVM server to talk with the function server. And this, but that said, the JVM server itself still handles all the interaction with the remaining of the serving stack, so that it know how to fetch data, how to do all this A/B testing, how to do logging. Everything is still happen there. So we were able to reuse most of the components we already have, but we allow you to author like Python-based function now. Yeah, I think that's all we want to talk about. And I think we are running out of time, but I guess you can find us in the happy hour. We can answer any questions.